For today, Data Communications and Network 1 class, this is lecture 21, chapter 11, part 2, High-Speed Ethernet. We will talk a little bit about the techniques of CSMACD first before we get into the high-speed Ethernet. Okay? So we will continue from last time. Here. Okay, so last time we talked about the Aloha and CSMA, okay, and CSMACD about the persistent techniques, okay. Today we will talk about the examples of the CSMACD transmission, okay. From here you can see that there are three stations, okay, station A, B, and C, connected to the Ethernet bus, okay, on the medium, and A and B and C, they are at the distance of d meters apart, okay. If B want to send something, okay, to A and B transmit to, suppose B want to send to A, okay, B also have to transmit both to A and both to C. So you can see that if you look at in the time, space-time diagram, okay, the time is on the vertical axis, okay. You can see that at time equal to 0, we have the B start to transmit the frame, okay, and B, the signal from B will reach station A and C at time TP, the propagation time. Look at it this way, probably easier. Okay, so this is station B transmitting, okay, so transmit to A and to C, okay. Now A starts transmitting at time t equal to 0 here, okay, so it's transmit to A and to C, okay. Even though it's the destination is C, you have to transmit both ways, okay, because everyone in the land has to see it. It's a broadcasting techniques. This one arrived at t equal to t sub p, which is the propagation delay time, okay. So suppose it takes 1 microsecond to arrive at A, okay, so t equal to 1 microsecond here. And B, that's a frame, right? So the first bit, okay, arrive at this time, and the last bit arrive at this time, okay. So this is the time of the frame that B is transmitting, okay. So you can look at it like transmit in terms of a frame, like this, okay, going this way, and this is like a frame, okay, and you have so it's arrived here. So this is a frame, okay. So in terms of this is a time, the time axis, okay. Now, if at this time, okay, between the time of t equal to 0 and t equal to tp, okay, between this time, C start to send, okay, C want to send something, okay, so C will just sense whether there is anything inside of the that is transmitting right now. C didn't see anything, okay, in the line because the signal from B will arrive at time equal to t sub p, right? So if C want to, suppose C want to transmit at time t equal to 0.5 microsecond, okay, and t sub p is equal to 1 microsecond, okay. So at this time, C listen to the medium, okay, and it looks like the medium is free. So C start to send the frame, okay. So C start to send the frame. Then when C arrive here, okay, at this point, it will you can see that it's arrived at B. B will see a collision, right? Because there is a frame from other user, okay, arrived at B. So B listen to the medium. B knows that there is B signals and also the signal from other users, okay. So there's a collision here. So when B sees a collision, okay, B see collision, B will stop sending the data, okay. B see collision, B stop sending the data. oh, okay, this is clear. Okay, so BC collision, B stop sending the data, and then at this time, when we arrive at frame B, arrive at station C, okay, at the medium is arrived at this point. So station C will see that, oh, there is collision because there is other users' signals coming, okay. So C will see the collision at this point, okay, and C will stop sending the data. So C frame will just stop here. C send up, okay, from this t equal to 0.5 microsecond to t equal to 1 microsecond, okay, and C will stop sending, okay. So this is the collision that occur, okay, collision that occur, and you can see that because C, B, and C stopped when it see the collision, okay, this is the CD, the collision detection techniques in the Ethernet, okay. So we will shorten the collision time, okay, because if you don't have collision detection, okay, if you have only the CSMA, the carrier sense multiple access, okay, what happens is that B will continue sending, okay, until the end of the frame, okay, and C also continue sending until it's end of the frame. So the collision will be much longer than this, okay. I can show you, for example. If you have only CSMA, okay, if you have only CSMA and not CSMACD, okay, what happens is that when B sent here, suppose this is B frame, okay, and B arrive here. So this is a B frame. Okay, then and C sending at this time. So it doesn't see the it sends the medium, okay, and it seems like this is free, so it's sent. And suppose this is C frame, okay. You can see that it will collide at this point if C does not listen to the medium after it transmits, okay, which means that it uses only CSMA and no CD, okay, no the collision detection. This is the collision, okay, collision will be for the whole period here, okay, for the whole period, okay. But if you use CSMA CD, if you use with the CD, okay, at this point it will stop sending. At this point, this one will stop sending. So this is the collision period, okay. So collision time is reduced, okay, from this, okay, the whole time of the transmitting frame, okay, into a smaller time here, okay, and so the channel will be free after this point, and you can sending after this point, okay, after the channel is free. In the sheet, you can see that there is an example and also in explaining, okay, that B is sending at time t equal to 0, and then a little while later, C is ready to sends the medium first, and found that medium available. This is what I was telling you about. Okay, so C send data out, collision occurs between B frame and C frame, okay. During this location, okay, between location of B and C, they start to collide. When it's learned about the collisions, it stops sending the data, okay. Okay, now what another thing is that we want to know is that what is the vulnerable time, okay, that they may have collision, because you listen to the channel, okay, but why you still have collision, okay? That's because you set at almost the same time, okay. But if C sent at a little bit different time, okay, there will be no collision, okay. So if you have here this is t equal to t sub p. Okay, so if C want to send, okay, at time, if C is ready to send the data at time more than t sub tp, t more than t sub tp, there will be no collision because no collision, okay? Because C will send the channel first, and you will see that, oh, okay, there are some signal coming, okay, there are signal coming, okay, so so you see that there's some signal coming, so it will not send, okay, so there will be no collision. So now we want to find the time, okay, that will cause no collision, okay. So if B want to send at time t equal to 0, okay, and C want to send at after TP, no, that is okay, right? So not okay, which means that there is collision when C want to send at t equal, sorry. When C want to send during the time t, okay, minus tp to tp, okay. So I'm telling you that there will be collision occur, okay, if C want to send during this time minus tp to tp, okay. So let's see, if C want to send from t equals to 0, have problem, right? Have problem, collide, okay? More than 0, collide, okay? If send over this time, collide, this collide, okay? Up to this point, if C want to send at this point, it will hear that there is something in the medium, so it will not send. So after this time is okay time. Okay, so if it's more than or equal to TP, it will be okay. Then if what happens if, okay, I'm telling you minus TP, right? So let's say T equal to minus T sub P. So if C want to send at this point, collide, okay? Until at this point, if T send at T equal to minus TP, okay? What happened? What happened is that this one, okay, will hear, okay, if C send, want to send, okay, before this, if C sending before this, less than minus TP, okay, what happened is that when C transmit, when it transmit over here, B will hear that there is something in the medium, so B will not transmit, so there will not be collision, okay, so the problem is this time. Okay, minus TP to TP is the time that is, if C send in this time, okay, it will collide. It will have a collision. If C transmit from minus TP to TP, there will be a collision. But if, you can also say like this to be safe, okay, so minus TP to TP, there will be a collision. If sent before, okay, or after this, there will not be collision, because if C sent before minus TP, B will not send, because we will see the frame from C before it transmit, okay? And if C want to send after T sub P, then C will hear the signal from B and C will not send, okay? So this is the time that we call it vulnerable period, okay? That even if you use the Ethernet, you use CSMACD, you can still have collision. So this is the time that you have to concern about. Now, if the propagation delay is very small, okay, because the LAN is a short distance, right? So if the propagation delay is small, what happens is that TP will be very, very small. So the vulnerable period, the total vulnerable period equal to 2 times of the TP seconds, okay? So if TP is very small, the vulnerable period is very small. and you have a very low probability of colliding because they send in this period. Okay, so this is the Ethernet. Okay, this CSMACD is a technique for the Ethernet, and so if you have the this is what I told you. The 1 hour period is 2 times t sub p seconds. Now let's look at some examples. Okay. Suppose there are 5 stations, and they are equally spaced. Okay, so you have 1, 2, 3, 4, and 5. Okay. Use the CSMACD Ethernet. Okay. With the TP equal to 0.1 millisecond for d meters. So adjacent channel or adjacent users, okay, has the difference of d meters apart. Now the frame allow TF, okay, the frame time equal to 20 milliseconds. Okay, so you see that usually the frame time is much higher than the propagation delay time. Now what happened? Now suppose station 1, 3, and 4 want to send at t equal to 0, 1, and 20. Okay. Station 1 want to send at t equal to 0 second. Okay. Station 2 at t equal to 1 millisecond. Station 3 at t equal to 4 millisecond. Okay, what happened? Okay, so station 1 sent, so it transmit at this time t equal to 0. Okay, the channel is free, so it starts transmitting. Okay, this is t equal to 0.4, right? 1, 2, 3, 4. 0.4 millisecond. Okay, now to want to send at 1, so this is arrive at 0.2 millisecond. Okay, frame from station 1 arrive station 3 at 0.2 millisecond, time equal to 0.2 millisecond. So station 2 want to send at 1 millisecond, right? It come and listen to the channel. Oh, okay, someone is transmitting, so it will not transmit. Okay, so even though station 3 want to send at t equal to 1 millisecond, it will not transmit. Okay, it will not transmit because someone is transmitting. Now station 4 come and at 4 millisecond. Okay, it will also not transmit because it's here that the transmitting is still going on. Okay, so no collision. Now if station 5 want to transmit at 0.2 millisecond, what happened? There will be a collision, right? Because this one at t equal to 0.2 millisecond, it starts sending. .2 arrive here 0.3, okay. So when it starts sending, okay, when t equal to 0.2 millisecond, station 5 will stop, okay, because it's the collision here, so you will stop sending. Stop, okay, so it sends only this frame. How about station 1? Station 1 see the collision at this point. This one start at 0.2 millisecond, right? So delay, this is 0.3 millisecond, 0.4 millisecond, 0.5 millisecond. This is 0.6 millisecond, okay? So this one will stop sending. Okay, this one stopped sending, so it stopped at, this is 0.6 millisecond, so 0.7, 0.8, 0.9, this is 1 millisecond. Okay, so so there is a collision here. Okay, this is a time, there's a collision. Okay, but after t equal to, okay, what is this time? This is 0.4, right? 0.5, 0.6, 0.7, 0.8. This is 0.8 millisecond. Okay, so but after t equal to 1 millisecond, okay, after t equal to 1 millisecond, channel is free again. Okay, so even though there's a collision here, okay, the channel is free again after t equal to 1 millisecond. So if so it's free again. So if station, let's say station 4 now want to send at t equal to 4 millisecond, right? So if it's 4 milliseconds here, it can start sending, okay, because channel is free again. Okay, so that's some examples, and in class I will give you more examples on this. Now let's look at the standard, okay, of the IEEE 802.3, okay, 10 megabit per second specification for Ethernet, okay. As I told you before, there is 10 base 5 and 10 base 2, okay, which is the first number is 10 megabit per second, okay. Base is stands for baseband, and 5 is 500 meters cable length, okay. 2 is 200 meters cable length, okay. And this is some of the standard, okay, in the physical layer, okay. We have the medium, okay, can be coaxial cable, okay. We can have the unshielded twisted pair, which is 10 base T. This is twisted pair, and we can have optical fiber. It's become 10 base FP, okay. So fiber pair, optical fiber pair, and we use Manchester, okay, as a signaling techniques, okay. We use the topology for the 10 base 5, 10 base 2 are bus, okay, but 10 base 3 are star. We have the segment length, we have the node per segment, we have the cable diameter, okay. So this is some specification that you can look it up by yourself, okay, for different standards. Now let's go to the high-speed Ethernet, okay. High-speed Ethernet is used, okay, a lot, okay, for LANs, okay. Is a broadband access, okay, and it's used for like data center networking, okay, because this is high speed, right? It can also use for the backbone of the local area network, okay. And this is very popular, okay. The Ethernet, as I told you before, we focus on this type of LAN because a lot of people are using it today. It is good because it's reliable, but it's not expensive, okay. And there's a lot of players, okay, a lot of vendors who build the device and they are compatible, right? So they are competitive and the price is low. We have the high-speed Ethernet. We call it like if it's 100 megabit per second, we call this fast Ethernet, okay? So 100 megabit per second is fast Ethernet. If it's 10 megabit per second, it's just the normal Ethernet, okay? And then after the fast Ethernet, we have the Gigabit Ethernet, 1 gigabit Ethernet, okay? And we have 10 gigabit Ethernet, okay? From the 10 gigabit Ethernet, we will use switching, okay, instead of the CSMACD. Okay, so at this point, we change to switching techniques. And we also have 40 gigabit and 100 gigabit per Ethernet, okay, and then higher and higher. Now for the fast Ethernet, this is a commonly used Ethernet, okay? This is low cost, okay? And we can transmit, okay, with the 100 megabit per second rate, okay. And you have a lot of medium choice. For example, we have 100 base X, 100 base TX, okay, which is this is a specification that you can see. You can see that you have 100 base TX is the shield twisted pair, right? STP is the shield twisted pair, and then you have the UTP, category 5 UTP, okay, and shield twisted pair. You have the, if it's 100 base FX, okay, it's optical fibers. If it's 100 base TX, again the 100 in front, the first number is the data rate, okay? So 100 megabit per sec, okay? Base is baseband. The T4, FX, TX, they are the medium, okay, that we are using, okay? So for the signaling technique, okay, we use MLT3, we use 4B, 5B, and RCI, okay? For this standard, you can also search, okay? We talked about NRCI before, but for the other, you can search, okay, on what it look like. Okay, this is similar to the digital to digital encoding technique that we have talked about, but it may have some more specific, right? Now they have the maximum signal segment length, which is 100 meters, and the network span. Okay, the one that uses the fiber optics has the highest network span, the longest network span. Now for the Gigabit Ethernet, okay, this is developed in 1995, okay, and still use CSMACD, okay, the same as the Ethernet format, okay, as a 10 and 100 megabit per sec, okay, but it specified the new medium, okay, it use 1,000, again 1,000 is 1,000 megabit, which means 1 gigabit, okay, so is this one use multimode fiber optics, okay. And again, you can see the book. You can also see search internet for the standard. Okay, there's examples is other than the 1,000 base SX, there's also 1,000 base LX. Okay, and this is the standard. Okay, you can see that for the LX. Okay, this is like long distance. Okay. So 1,000 base LX, you use single mode fiber, okay? You use a single mode fiber, multi-mode fiber. If you use single mode fiber, you can go up to 5 kilometers, okay? If you use multi-mode fiber for LX, you can go up to about 500 meters. For the SX, okay, this is shorter distance, okay? So in the SX, you use multi-mode fiber, okay? And go to about 250 meters or 500 meters. For the 1,000 base T, okay, T is the unshielded twisted pair. This one use category 5 UTP, okay. This is less than 250 meters, so shorter. And then CX is the shielded cable. This one we can go up to only 25 meters, okay. So this is shown in the log scale, okay. And you can see that we change the medium, okay, we use the same techniques, but we change the medium, we can send to make it like bigger LAN, okay. The next one is 10 gigabit per sec, okay, Ethernet. There are many different alternatives, okay, of physical configuration for this case. If you want to use a longer make a bigger LAN, okay, want to have a longer segment, okay, you can use repeater as I told you in previous video, okay, we can join segments together, okay, by using a repeater, and the repeater will be like transparent to the user. The user will think that it's the same LAN, okay, it doesn't know that it comes from a different segment, okay. Now, the standard, okay, for 10 gigabit Ethernet is the IEEE 802.3 AE 2002, okay, because it's come out in 2002. And this is currently it's like about 2 years ago, okay, it's the fastest of the Ethernet standard. But now there are more faster standard, okay. This one use switching techniques, okay. So sometimes it's called switch Ethernet, and so it doesn't use CSMACD anymore. We have the 10 gigabit base short base S, which is short, and 10 gigabit, okay. So this is 10G. 10G means 10 gigabit per sec, okay, because the number 0 is too low, too many already, okay. So let's go to 10 and then 100 and then 1,000, okay, now it's like 10,000, so change it to 10G, okay, and then base is baseband. And because you have the Ethernet, okay, Gigabit Ethernet, okay, the other standard become obsolete, okay, because people don't want to use them anymore. Because, I mean, Ethernet is cheap and you have a lot of speed, okay. So in the past, I used to talk about the token ring more and also fiber distributed data interface, okay, which is 802.4 and 802.5, but right now, most of the people use Ethernet, okay. This is examples of the 10 gigabit per sec Ethernet configuration, okay. You have the backbone switch, and then you have workstation, you have the, so at the backbone, okay, you use 10 gigabit per sec, but at the users, okay, you may allow only maybe like 10 or 100 megabit per sec, okay, for each of the users. This is the 10 gigabit Ethernet distance option, okay. If you want to send to like 40 kilometers, okay, you want to send to 40 kilometers, okay, you have to use the single mode fiber definitely, and also the 10 gigabit base E, okay, this like extended distance, okay, which use the wavelength of the signal 1550 nanometers, okay. For the 10 kilometers, you can use the single mode fiber 10 gigabit base L, which is the wavelength of 1310 nanometers. If you use, you can see that for all the long distance, you use single mode fiber, okay, single mode fiber. But for the shorter distance, you can use the multi-mode fiber, okay, which is cheaper. So there are the suffix, okay, SLELX4. This is to is a spec for like different physical medium. Okay. Now the 100 gigabit per sec Ethernet. Okay, this was under development since November 2007, and so this is kind of the newer standard. Okay, as I told you before, the IEEE 802.3 standard was approved in 2014. Okay, and there's the product start to come out in 2012, and this is applications we can use for the data center, internet media provider. That was like one very high demand, okay, on the multimedia traffic through the internet, okay. So you can handle like extremely large traffic flow. So over here in the middle, you can use like 10 gigabit Ethernet as a backbone, okay, and then you have 100 gigabit Ethernet as a backbone, and you can see that it will be called like 100G, okay. So anyway, so this is like 100 gigabit Ethernet, okay. So this is like a massive server side. Okay. Now let's look at the media option for the 40 gigabit Ethernet and the 100 gigabit Ethernet. Okay. You can use like copper, multi-mode fiber, single mode fiber. Okay, and you have the 1 meter, 10 meters, 100 meters, 10 kilometers, 40 kilometers. Okay, that you can transmit. For the 100 gigabit per sec, you can transmit through the 40 kilometers. Okay, with the 1000 G. Okay, which is I think this is something wrong here. Okay, it should be 100 G. Okay, I think there's a typo here. 100 G baseband ER4. Okay, this is from Starling book. I think there's a typo there. Anyway, you have short reach, long reach, and extended long reach. Okay, and you have the coding scheme is the 64B/66B block coding. Okay. Okay. So that is the end of this video, and then for the next video we will go to chapter 12, which is the Internet protocol. Okay, thank you.